Hi, my name is Michael Pendazis. This is Math 231, Linear Algebra, online lesson number 8. Today we will be doing 4.7 to 4.10. So we'll be finishing chapter 4. Let's get started. So 4.7 is titled Row Space, Column Space, Null Space, and Null Space. Okay. And so we'll be focusing on the row space, column space, and null space in this section of the book. Okay, so first definition. Our first definition is for an m by n matrix. For m by n matrix A, the vectors in Rn formed by the rows of A are the row vectors of A. The vectors in Rn formed by the columns of A are the column vectors of your matrix A. Okay, so for this first definition, we're defining the row vectors of A and the column vectors of A, where A is an m by n matrix. Okay, and so an example of this definition would be if I had a 3 by 2 matrix A, 3 rows, 2 columns, and let's say that matrix looked like 1, 2, 3, 4, 5, 6, right? There's 3 rows, row 1, 2, 3, column 1, and column 2. So this is a 3 by 2 matrix, right? So the rows of this matrix, this would be R1, row 1. This would be R2, row 2. This would be R3, row 3. And so, right, so this matrix would be the first row vector. This would be the second row vector. And this would be the third row vector. Okay? And this would be the first column, and this would be the second column. And so the first column would be the matrix 1, 3, 5. And the second column would be the matrix 2, 4, 6. Make sense? Okay? And so these are the row vectors of A, and those two are the column vectors of A. Right? And because these are row vectors, these are 1 by 2 matrices. And these are 3 by 1 matrices. Okay? And so these are the columns, C1 and C2 are in R3. Okay? And so when we say the column vectors are in Rn, where it's an m by n matrix, here the column vectors are in R3, where 3 is the number of rows. And here these columns are R1, R2, and R3 are in R2 because it's a 1 by 2, they're 1 by 2 matrices. They have 2 components, and 2 is the number of rows, the number of columns are, right? And so the row vectors are in Rn, which is the number of columns in the original matrix A. Okay? So you might want to look at this a little bit longer, and so I'm just showing you what the row vectors and column vectors of the matrix are and the sizes of them. It's determined by the size of the original matrix A. Okay? Okay, so those are the rows and columns of the matrix. Row and column vectors of the matrix. The next definition is if A is n by n, if A is an n by n matrix, the subspace of Rn spanned by the row space, by the rows of A, is the row space of A. The subspace of Rm spanned by the columns of A is the column space of A. Okay? So we have the row space of the matrix A and the column space of the matrix A. Okay? So there's only one row space and column space for a given matrix A. Okay, so for instance, as an example of this, again, if you have the same matrix A, which is a 3 by 2 matrix from before, and we have 1, 2, 3, 4, 5, 6, this is our 3 by 2 matrix A, then the row space of A is going to equal the span of the row vectors of that matrix. So it's the span of R1, R2, and R3. R1 was this, R2 was this, and R3 was that. And so the row space of A is the span of the row vectors of that matrix. The column space of A is equal to the span of the columns of A. And so there's two columns of A. This is the first column, and that's the second column. And so the column space of this matrix is the span of its columns. All right? And so that's the row space and column space of a matrix, an example of one. And also adding to the definition, I'll write the definition again here. The solution space of AX equals 0 is the null space of A. Okay, so the solution space of this linear system is called the null space of A. Okay, so what it means, remember, the solution space of that matrix equation is the set of all vectors x that satisfy that equation for some given A. Okay, so if you have the set of all vectors x that satisfy that equation, make it true, that's the solution space of that equation. And so the solution space of this equation is called the null space of A. And so once you find the set of all solutions, it's already a vector space. And it's called the null space of A. It's closed under addition and it's closed under scalar multiplication. We showed that before. And so you don't need the span of it in order to create a vector space. You already have a vector space just finding the set of solutions. That itself is a vector space. You don't have to take the span of the solutions like you do up there. Okay, and so that's the definition of the null space of A. And so the definitions of row space, column space, and null space right on this board. Okay, so let's keep going. Okay, so now we know what those three spaces are. Okay. Next is a theorem, Theorem 4.7.1. And so this theorem says a system of linear equations AX equals B is consistent if and only if B is in the column space of A. Okay? So in this theorem, there's two statements that are equivalent. A system of linear equations AX equals B is consistent if and only if B is in the column space of A. And so it's saying this statement I squiggly underlined and that one are equivalent. They have the same truth value. Okay? Saying AX equals B is consistent means that there's at least one solution X for this equation. And again, that's equivalent to saying B is in the column space of A. Okay? And okay, so you could prove both directions. If you assume this was consistent, there would be a solution X, and then that would mean that B was a linear combination of the columns of A, which would mean it was in the column space. And if B was in the column space of A, that would mean there would be some solution X you could plug in. You could represent B as a linear combination of the columns of A, and so that would mean there would be a solution X. So there's a very quick proof of this theorem. Okay. The next theorem is theorem 4.7.2. If X naught is any solution of a consistent linear system, AX equals B, and if S, which is equal to V1, V2, up to including V sub k, is a basis for the null space of A, then every solution of AX equals B can be written as X equals X naught plus C1 V1 plus C2 V2 plus dot 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 plus CK VK. That's 3. Okay, and conversely, for all choices of scalars C1 to CK, the vector X in the formula for 3 is a solution of AX equals B. Okay, so this is theorem 4.7.2. If X naught is any solution of a consistent linear system AX equals B, meaning AX naught equals B, is true, and if S, this set, is a basis for the null space of A, then every solution of AX equals B could be written as X equals X naught plus C plus that. Conversely, for all choices of scalars C1 to CK, the vector X in 3 is a solution of AX equals B. And so what this equation tells you is the entire, all of the solutions to the original equation AX equals B. Okay? And so that's saying that all the possible solutions of AX equals B are of that form. X naught being a particular solution, and then this being a linear sum of the basis vectors for S. Okay? Okay, so all the solutions AX equals B are of this form. That's what this is basically saying. Given the condition, right, S is a basis. And okay. So this is, okay, so X naught is a particular solution, like I was saying, is a particular solution of AX equals B. And then the remaining part, and by remaining part I mean all of that, the remaining part is the general solution of AX equals 0. Okay? So the remaining part here is the general solution of AX equals 0, and this X naught is a particular solution of AX equals B. Okay? Okay, and so that's theorem 4.7.2. Okay, so more theorems. Good. Theorem 4.7.3. Elementary row operations. Do not change the null space of a matrix. Okay, so elementary row operations do not change the null space of a matrix. And so what that means, I'll put means here. That means if you have a system AX equals 0, right? The null space is the set of all solutions. If I take A and then through elementary row operations on A, right? If I take a sequence of elementary row operations in A and get the matrix A prime, then the equation A prime X equals 0 has the same set of solutions. That's what theorem 4.7.3 means. Okay? So the null space again of a matrix A is the set of all solutions X to AX equals 0. And so this theorem is saying elementary row operations do not change the null space of a matrix. It means if you take a matrix A and you form any sequence of elementary row operations on it and you get a matrix A prime, then the equation A prime X equals 0 has the exact same set of solutions X as the original AX equals 0 did. Okay, so that's theorem 4.7.3. Theorem 4.7.4. Elementary row operations do not change the row space of a matrix. Okay, so elementary row operations do not change the row space of a matrix. That's what that means is if you have so if you have a matrix A, right, and through elementary row operations, you take the A and you get A prime. So you start with A, you take a sequence of elementary row operations on it, and you get A prime afterwards. Then the span of the rows of A is equal to the span of the rows of A prime. Okay, right? The row space of a matrix is just the span of its rows. And so since the row space doesn't change after elementary row operations, you could start with matrix A, form a sequence of elementary row operations on it, get A prime, and then the span of the rows of the first thing is equal to the span of the rows of the matrix you get after those elementary row operations. So the span of the rows of A is equal to the span of the rows of A prime. That's the same as saying the row space of A is equal to the row space of A prime, because the span of the rows of the matrix is its row space. Okay, do not change the row space. Okay, so that's theorem 4.7.4. Example 4. Find a basis for the null space of the matrix A is equal to 1, 3, -2, 0, 2, 0, 2, 6, -5, -2, 4, -3, 0, 0, 5, 10, 0, 15, and 2, 6, 0, 8, 4, 18. Okay? And so we want to find a basis for the null space of this matrix. So solution, this problem is, well, the null space of a matrix is the set of all solutions of AX equals 0. And so we're going to find the solutions to AX equals 0, and that's going to be a vector space, and we're going to find a basis for that vector space. Okay? So, I guess my plan here is just the null space of A. I'm not going to go into all that work. The null space of A is the solution space of AX equals 0, right? And that has a basis of V1, which is equal to -3, 1, 1, 2, 3, 4, So basically you take AX equals 0, find the general solution to AX equals 0 using parametric equations, right? Represent it using matrices. And then you can see it's a linear combination of parameters as scalars times these vectors. And so when you get the general solution, you can represent it as a linear sum where the coefficients are the parameters you chose. And so the vectors involved are the basis vectors of your vector space because they span your space and they're linearly independent. Okay, so that's V1. Then V2 is -4, 0, -2, 1, 0, 0. Okay, so V1, V2, and V3, those are the three vectors that not only span the solution space, but they're linearly independent, and so that they form basis for the solution space of AX equals 0. They form basis for the null space of A. Okay, so that's example 4. Good. Theorem 4.5.7. If a matrix R is in row echelon form, then the rows of R with leading ones, those are the non-zero rows, form a basis for the row space of capital R. And the column vectors with leading ones form a basis for the column space of R. And so that's theorem 4.5.7. Oh, sorry. It's theorem 4.7.5. Okay? So if matrix R is in row echelon form and the rows of R with leading ones form basis for the row space of R, and the column vectors with leading ones form basis for the column space of R. Okay, so that's theorem 4.7.5, and then in example 6, let's see what that means. Okay, so in example 6, we're going to find a basis for the row space of this matrix A, which is equal to 1, -3, 4, -2, 5, 4. And that's 2, -6, 9, -1, 8, 2, 2, -6, 9, -1, 9, 7, and then -1, 3, -4, 2, -5, -4. Okay? So we want to find basis for the row space of that matrix. Okay? So if we reduce this to row echelon form, meaning we perform an appropriate sequence of elementary row operations on A to get it to row echelon form, not necessarily reduced row echelon form, but at least row echelon form, then we'll get this matrix 1, -3, 4, -2, 5, 4, 0, 0, 1, 3, -2, -6, 0, 0, 0, 0, 1, 5, and then all zeros in the last row. Okay? And so I'm going to call this matrix R. The whole matrix R. Okay? So we start with A. We want to find a basis for its row space. And we get it to row echelon form through an appropriate sequence of elementary row operations. We get it to row echelon form, and we call that matrix R. Okay? And so now that's that. Okay? So now, right, here's the... So in Theorem 4.7.5, it says, if a matrix R is in row echelon form, the rows of R with leading ones form a basis for the row space of R. So the first three rows are rows with leading ones, right? This is a leading one, that's a leading one, and that's a leading one. There's three leading ones. The fourth row is all zeros, and it doesn't have a leading one. So the first three rows have a leading one, and those are the rows that will form a basis for the row space of R. And so I'm going to call this first row R1, the second row R2, and this third row R3. Those are the first three rows of matrix capital R, not A, capital R. And so those three rows will form a basis for the row space of R. Okay? So by Theorem 4.7.5, the set R1, R2, R3 is a basis for the row space of R. Alright? So does that make sense? So the theorem right above this example says that all the rows with leading ones of a matrix in row echelon form form a basis for the row space of that matrix. And so rows 1, 2, and 3 being the only rows with leading ones, those three, the set with those three rows in it, is a basis for the row space of that matrix R in row echelon form. Now in the previous board I said that elementary row operations do not change the row space of a matrix. And so these elementary row operations we did on A to get R did not change the row space of A. And so this matrix A had a certain row space, and we performed elementary row operations on it to get the matrix R. Well, that means that the row space of A was unchanged, and so that means the row space of R is the same as the row space of A. And so if this set is a basis for R, for the row space of R, and it's the same as the row space of A, that means this also forms a basis for the row space of A. Okay? Also, by R1, R2, R3, it's not the first three rows of A, it's the first three rows of R. Also, the set R1, R2, R3 is a basis for the row space of A. Since elementary row operations do not change the row space of a matrix. Okay? And so since we got R from doing elementary row operations A, the row spaces are the same. And finding a basis for the row space of this is the same as finding the row space, a basis for the row space of that. And we're done. And then that's the answer to example 6 in 4.7. Okay. Okay, so the next theorem is Theorem 4.7.6. And so that theorem says if A and B are row equivalent, matrices, then, and remember, row equivalent matrices mean that if I take either matrix, I can perform, there's some sequence of elementary row operations on either matrix in which I can get the other one. That's what it means for two matrices to be row equivalent. Right? And if A is row equivalent to B, that also means B has to be row equivalent to A. And so saying one matrix is row equivalent to another, we just say that the two of them are row equivalent to each other, because one implies the other. Right? And so that's why the assumption is A and B are row equivalent, not one is equivalent to the other. Okay? So if A and B are row equivalent, then part A says a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. So a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. Okay? So if you have matrices A and B that are row equivalent, that means that if you take any choice of column vectors of A, if you take equivalently the same numbered columns of B, they're either both linearly independent, both set of column vectors, or they're both not linearly independent. Okay? So either both are or both aren't a set of linearly independent vectors. Okay, and then B, so for instance, if you take the first, second, and fifth columns of A, you would take the first, second, and fifth columns of B. And either the three columns in each make up a set of linearly independent vectors, or each set of three vectors is not linearly independent as a set. Okay, with part B, a given set of column vectors of A forms a basis for the column space of A if and only if the corresponding column vectors of B form a basis for the column space of B. Okay, so a given set of column vectors of A forms a basis for the column space of A, if and only if the corresponding column space of B forms a basis for if and only the corresponding column vectors. Sorry, this is vectors here. Okay. That word's vectors there. Okay. So a given set of column vectors of A forms a basis for the column space of A, if and only if the corresponding column vectors of B form a basis for the column space of B. Okay? And so in A, we're talking about linearly independence. In B, we're talking about bases. Okay? Okay, it's just like A, except now we're talking about bases. So if we have a matrix A, and we choose the first, second, and fifth columns of A, okay, and then we have a row equivalent matrix B, and we choose the same columns, the first, second, and fifth columns of B. We have the first, second, and fifth columns of A and B, the matrices are row equivalent. Then either both set of three vectors are bases, or they're both not bases of the column space of their respective matrices. And so either columns 1, 2, and 5 of A form a basis for the column space of A, and columns 1, 2, and 5 of matrix B form a basis for the column space of B, or neither of those three vectors form a basis for the column space of the matrix that they're in. Okay? Okay. Okay, so now let's do example 7. Example 7. Find a basis. Find a basis for the column space of A, which is equal to 1, -3, 4. Okay, so find a basis for the column space of that matrix A that consists of only columns of A. Okay, so we want to find a basis for the column space of A that consists of only columns of A. Okay, so this is the first column, that's the second column, that's the third column, that's the fourth column. that's the fifth column, and that's the sixth column, right? And so the span of those 6 columns is the column space of that matrix, right? The set of all linear combinations of those 6 columns is the column space of A. That's what it means to be the span of the column vectors of the matrix, right? It's a set of all linear combinations of those 6 vectors, okay? So we want to find a basis for that column space. We want to find a subset of those column vectors which spans the entire column space by itself and is linearly independent. Okay, and so here's the solution. Okay, so this matrix R is the row echelon form of that matrix A. It's 1, -3, 4, -2, 5, 4. Okay, so if you do a bunch of math in this A and you do an appropriate sequence of elementary row operations on it, you can get it to row echelon form. Right, and there's lots of row echelon forms, and this is one of them. So, so this is one of the row echelon forms of that matrix A. Okay, so I mean there are infinitely many row echelon forms to this matrix, but this is one of them. Okay, so this R is one of the row echelon forms of that matrix, which is attained by doing an appropriate sequence of elementary row operations on A to get R. Okay, right. So it satisfies all 3 conditions for a matrix to be in row echelon form. Okay, so this R is in row echelon form. This is the row echelon form of A. Okay, and so by our previous theorem, part B, if we find a set of column vectors of R that forms a basis for the column space of R, right? So if we find a set of column vectors of this matrix R that forms the basis for the column space of R, then the corresponding set of column vectors of A forms a basis for the column space of A. Okay, so for instance, if you choose the right columns of R to form a basis for the column space of R, the corresponding same number choices for the columns of A will form basis for the column space of A. And so we boiled the problem down to finding the right columns of R to form a basis for the column space of R, right? But we know what those are. We know what the leading ones of R are. And so by previous theorem, the corresponding the columns of R that contain all the leading ones of the matrix, all those columns, that forms a basis for the column space of R. Okay, R has to be in row echelon form, and when you get a matrix in row echelon form, all the columns with leading ones, those form a basis for the column space of that matrix. So columns 1, 3, and 5 form a basis for the column space of R. And by what I wrote here, that means the corresponding choices of columns of A form a basis for the column space of A. And so the first column of A, the third column of A, and the fifth column of A, those will form a basis for the column space of A. Okay? Those are the corresponding column vectors of A to the column vectors of R I chose there. The first, third, and fifth. Okay? And so that's the answer. We found a basis for the column space of A is the first, third, and fifth columns of A. And they only consist of column vectors of A. That's example 7. Okay? Okay. Example 9. Find the basis for the row space of A. Find a basis for the row space of A, which is this matrix. 1, negative 2, 0, 0, 3, 2, negative 5, negative 3, negative 2, 6, 0, 5, 15, 10, 0, 2, 6, 18, 8, 6. Okay, so find a base for the row space of that matrix. Okay? Consisting entirely of row vectors of A. Okay, so I want to find the basis for the row space of that matrix, consisting entirely of row vectors of A, right? Again, the row space of this matrix is the span of the rows of the matrix. And so the span of the 4 rows of this matrix is its row space. We want to find a basis for that row space. Once you find the row space of a matrix, it is a vector space. It's closed under addition and scalar multiplication, and so it's a subspace of some power of some n space. Okay? Okay, so you can show that the row space of a matrix is closed under addition and scalar multiplication, and so the row space is a subspace of Rn, making it a vector space. So the row space of a matrix is a vector space. Okay? So we want to find a basis for that vector space. Okay. 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 So if we start with A, and if we take its transpose, okay. So we start with A and we take its transpose, and then we take that transpose and we get it to row echelon form using only elementary row operations. We obtain this matrix. So that's A. Now take its transpose and then take the transpose and get it to row echelon form. And so the reason why we're going to take the transpose first now is because when we do the same thing we did in the last example to the matrices transpose, we're going to find a basis for the column space of A transpose this way. And so finding a basis for the column space of A transpose is the same as finding a basis for the row space of A. A transpose is switching the rows and columns of a matrix. And so by the last problem, we have a procedure for finding a basis for the column space of a matrix, right? Not for the row space of a matrix. And so we can just apply the same method for finding a basis for the column space of a matrix, but by finding the column space of the transpose of a matrix. And by finding the column space of the transpose of a matrix, we're finding a basis for the row space of the original one. Okay, because the rows of A will become the columns of A transpose. And so what we find out about the columns of A transpose, we're finding about the rows of the original matrix A. Okay? So we're going to find a basis for the column space of A transpose. So the goal is find a basis for the column space of A transpose. That will be a basis for the row space of A. And we will only be using columns of A transpose for the column space of A, for a basis for column space of A, which will then correspondingly be rows of A, which will form a basis for the row space of A. Okay? We want to consist entirely of row vectors of A. We only want rows of A to form a basis for the row space of A. Okay? Okay, so we're going to try to find only columns of A transpose that form a basis for the column space of A transpose, and that will be only rows of A which form a basis for the row space of A. Okay, and so to do that, we take A transpose and get it to row echelon form using an appropriate sequence of elementary row operations, and then the columns of I'm going to call this R. That's A transpose in row echelon form. That's R. Taking all the columns of R that have leading ones in it, those are the columns of R that form a basis for the column space of R. So columns 1, 2, and 4 form a basis for the column space of R. And correspondingly, columns 1, 2, and 4 will form a basis for the column space of A transpose. And so the C1, C2, and C4, this is C1, this is C2, and this is C4. C1, C2, C4 forms a basis for the column space of R, okay? So C1, C2, and C4 form a basis for the column space of R, right? And so, by what we did before, the first, second, and fourth columns of A transpose will form a basis for the column space of A transpose, okay? And so that implies that the first, second, and fourth columns of A transpose form a basis for the column space of A transpose. Okay, so first, second, and fourth columns of A transpose form a basis for the column space of A transpose, and that implies that the first, second, and fourth rows of A form a basis for the row space of A. Okay, so the first, second, and fourth rows of A form a basis for the row space of A, and we're done. That's what we want to find. We want to find a basis for the row space of A consisting entirely of row vectors of A. And so that means we'll choose the first, second, and fourth. And so that will be the first one here, the second one here, and the fourth one here. The first, second, and fourth rows of A are the basis for the row space of A. They're linearly independent, and they span the entire row space of that matrix. Okay? The span of only those three vectors, the first, second, and fourth, is equal to the span of all four vectors. Okay? And they're linearly independent. So they form basis for the row space of that matrix. Okay? And so that is the end of that problem, example 9. Okay, so that's the end of 4.7. Okay. So 4.8, the rank, nullity, and fundamental metric spaces. Okay. So 4.8 is rank, nullity, and fundamental metric spaces. I may have to change my marker. So, theorem 4.8.1. The row space and column space of A have the same dimension. Okay, so that's theorem 4.8.1. The row space and column space of A have the same dimension. Okay, the row space of matrix A, again, is the span of its rows. The column space of matrix A is the span of its columns. They're both vector spaces, right? They satisfy all 10 axioms for a vector space. So the row space of matrix and the column space of matrix are both vector spaces. Vector spaces have a dimension. The dimension of a vector space is the number of vectors in any basis for that vector space, right? Every basis, a vector space has infinitely many, possibly infinitely many bases, right? Except the zero vector space only has one, the empty set, right? That only has one, but other ones have infinitely many. So if you take any vector space, any basis of any vector, if you take a fixed vector space, any basis for that fixed vector space has the same number of vectors in it. That number is called the dimension of that vector space. And so the row space and column space of a matrix are both vector spaces, and by this theorem, it shows that they both have the same dimension. Both the bases of both vector spaces each have the same number of vectors in it. Okay? So that's theorem 4.8.1. Okay, definition 1 in this section. The common dimension of the row space and column space of a matrix A is the rank of A. Okay, so the column dimension of the row space and column space of A is the rank of A, denoted by rank of A. So denoted by rank of A, okay? So so the common dimension of the row space and column space of A is the rank of A, denoted by rank of A, okay? The dimension of the null space is the nullity of A, denoted by nullity parentheses A. Okay? So the common dimension of the row space and column space of the matrix A is the rank of that matrix A, denoted by rank of A. The dimension of the null space of A is the nullity of A, denoted by that symbol. Right? So, okay, so the row space and column space of the matrix has the same dimension. That common dimension is the rank of that matrix A. Right? Remember, the null space of a matrix is the set of all solutions X that satisfy the equation AX equals 0. So that set of solutions to AX equals 0, that's the null space. The null space is a vector space, right? It's a subspace of Rn, or some power of R. I could just say Rn. That's a subspace of Rn. It's a vector space. It has a dimension. We call the dimension of the null space of A the dimension of the vector space of solutions to AX equals 0. We call that dimension the nullity of A. Okay? Again, the nullity of A is the dimension of the vector space of solutions to AX equals 0. Okay, so that's definition 1, the rank of a matrix and the nullity of a matrix. Okay. Good. Okay, so example 1. Find the rank and nullity of this matrix. Find the rank and nullity of this matrix A, which is negative 1, 2, 0, 4, 5, negative 3. It's time to change markers. We'll go blue. So the blue marker is just going to continue where I left off. 3, negative 7, 2, 0, 1, 4. Okay, so to find the rank and nullity of that matrix A. Okay, so we're going to find the rank and nullity of that matrix A. Okay, so we're going to find the rank and nullity of matrix A. So the reduced row echelon form of A is, so if we start with A and we get to reduced row echelon form, okay, then we get the matrix R, and that matrix R is equal to this matrix. 1, 0, negative 4. Negative 28, 37, 13, 0, 1, negative 2, negative 12, negative 16, 5. Everything else is zeros. The other two rows are zeros. Okay, so we get this matrix R. It's the reduced row echelon form of A, right? There's only one reduced row echelon form of a matrix, right? There could be infinitely many row echelon forms. There's exactly one reduced row echelon form. Okay, so that's the reduced row echelon form matrix A. Okay, so again, so if we look at the rows of R that have leading ones, there's only two rows, there's exactly two rows of R that have leading ones. And so the rank of R is 2. Okay, so the dimension of the row space of R is 2. The row space of A and R is exactly the same because elementary row operations do not change the row space of a matrix. So because the row space of A and R are the same, knowing that the dimension of this row space is 2 means the dimension of the same row space of A is 2. And so that means that the rank of A is 2. That's the dimension of the row space of A. It's equal to the dimension of the row space of R, which is 2, because there's 2 rows of R with leading 1s. Okay, right? These 2 vectors form a basis for the row space of R. We now have a basis with 2 vectors in it. The dimension of the row space is 2. Okay, so the rank of A is 2. Not only is the row space 2-dimensional, the column space is also 2-dimensional. Okay, because the row space and column space have the same dimension from the earlier theorem. Okay, now when you find the solution space of AX equals 0, you get a linear sum with 4 vectors in it. Okay, so the general solution of AX equals 0 is x1, x2, x3, x4, x5, x6. It's R is R times, I'm going to go to black now, 4, 2, 1, 0, 0, 0, plus S times this vector, 28, 12, 1, 0, 0, plus U, I use U here. U is negative 13, negative 5, 0, 0, 0, 1. Okay? So, so the general solution of AX equals 0 is that. And what that means is, right, if you find the general solution, right, you get this to reduce echelon form here, and then you find the parametric equations that describe the general solution, right, to this corresponding linear system, Rx equals 0. You could then represent those parametric equations as one matrix equation. And so this represents the general solution of AX equals 0. And so these 4 vectors form a basis for the solution space of AX equals 0. Finding a basis for the solution space of AX equals 0 is finding a basis for the null space of the matrix A. Okay? So finding a basis for the null space of A means count the number of vectors in your basis. That's a dimension of that vector space. And so this basis has 4 vectors in it. That means the dimension of that vector space is 4. That vector space is the set of all solutions to AX equals 0. That vector space is called the null space of A. The dimension of that null space is the nullity of A. The nullity of A is 4. Okay, nullity of A is 4. There's 4 vectors there. They're linearly independent and they span the solution space to AX equals 0. They span the null space of A. So it's a linearly independent set that spans the null space, and so it's a basis for it. Okay, you can see it's a basis because this has a 1 here, everywhere else is zeros. Here has a 1, everywhere else is zeros. Here there's a 1, everywhere else is zeros. Here there's a 1, everywhere else is zeros. You cannot express any of these 4 vectors as a linear combination of the other 3 because all 4 of them have a component, a non-zero component, where all the other ones are 0. Okay? Right? Here's is a 1, everywhere else is a 0. In that component, this is a 1, everywhere else is 0, there's a 1 there, everywhere else is 0, this is a 1, everything else is 0. So if I wanted to try to express this vector as a linear combination of all the other ones, I could not, because this is a 1 and all these are zeros. And if I take any linear combination of these 3, I would have to have a 0 here and there's a 1 there. So none of these 4 vectors can be expressed as a linear combination of the 3. That makes all 4 of them linearly independent as a set. Okay? Okay. Okay, let's keep going. Okay, so notes. Let A be an n by n matrix. The rank of A is less than or equal to the min of m comma n. Okay. Okay, so if A is an m by n matrix, that's what I mean by that. If A is an m by n matrix, the rank of A is less or equal to the min of m comma n. Okay? The rows of A are in Rn, and the columns of A are in Rm. And so the rank, the dimension of the rank of A, the dimension of its row space and column space, which are the same, right? The dimension of a vector space cannot. So if the rows of A are in Rn, right? That means its dimension, the dimension of the row space is at most n, but the columns of A are in Rn, and the dimension of the column space is at most m. So each space has a dimension at most m and n, but they're the same. And so if the dimension of both spaces are the same, and one is at most m and the other is at most n, they're both at most the min of m and n. Does that kind of make sense? So the row space and column space each have the same dimension. One of them, the dimension is bounded, one of them the dimension is the most m, and the other one the dimension is the most n. But they're both the same, which means both of them the dimension has the same dimension for both, has to be at most the minimum of m and n. If either one had a dimension larger than the min of m or n, that would contradict the fact that they're each bounded. They're both at most m and n, respectively. Okay. So the rank of A is less or equal to the min of m and n. So theorem 4.8.2. Dimension theorem for matrices. If A is a matrix, so if A has n columns as a matrix, then the rank of A plus the nullity of A is equal to n. And that's equation 4 in this section. And so this is extremely important. It's called the dimension theorem for matrices. So if A is n columns, then the rank of A plus the nullity of A is equal to n. Okay? Okay. So that's extremely important. Theorem 4.8.3. So if A is m by n, then part A, the rank of A is equal to the number of leading variables in the general solution of AX equals 0. Okay? And part B is the nullity of A is equal to the number of parameters in the general solution of AX equals 0. Okay, so the rank of A is equal to the number of leading variables in the general solution of AX equals 0. Okay, so the leading variables in AX in the solution, general solution of AX equals 0, the leading variables correspond with the leading ones of the matrix A in reduced echelon form. Okay. And the rows with leading ones, those form a basis for the row space of A. And so the number of leading ones in A in reduced echelon form, the number of leading ones is the number of non-zero rows, and those are the rows which will form basis for the row space. And so the number of leading ones is the number of rows that make up a basis for the row space. That number of rows is the dimension of the row space or the rank of that matrix. Okay, so the rank of a matrix A is the dimension of the row space of A. It's the number of vectors in any basis of the row space of A, right? And the number of leading ones is the rows with leading ones are the rows that form a basis for A in reduced echelon form. And so that's the number of vectors for the basis for the row space of A in reduced echelon form. For the row space of A in reduced echelon form, that's the same as the row space of A. So the number of leading ones is the dimension of the row space of A in reduced echelon form. It's the same as the dimension of the row space of the original matrix A. Okay. So the number of leading ones in general solution of AX equals 0 is the dimension of the row space of A, the rank of A. Okay. The nullity of A is the number of parameters in the general solution. Well, right. So the leading variables and the parameters, right? They have to add up to the number of columns of your matrix, and that's because each leading the number of columns in your matrix is the number of variables. It's an n by n matrix, so the number of columns is the number of variables you have. And so, if the rank of A is the number of leading variables, the rest of the variables are how many, the number of other variables is the number of your free variables. That's the number of parameters. And so if the total number of variables is n, right? If the total number of variables is n, then if you take n and subtract the rank of A, you'll get the nullity of A. But the number of columns minus the number of leading variables is all other variables. Okay, and that's the number of parameters. So the number of parameters is equal to the nullity of A, and you can use the last theorem for that. Okay, but without all that proof, you can just go by the theorem and say that the rank of A is the number of leading variables in that general solution, and the nullity of A is the number of parameters in the general solution of that. Okay, so you can use the theorems you can just take right from the theorems these facts on a test. You don't have to worry about the proof of these theorems. Okay. Okay. Let's go. Okay. Theorem 4.8.4. If AX equals B is consistent as a linear system, okay, is consistent, M equations, and unknowns, and if A is rank R, then the general solution of the system AX equals B, the general solution of the system contains n minus r parameters. Okay, so if AX equals B is consistent and has M equations and unknowns, and if A has rank R, then the general solution of the system contains n minus r parameters, right? Okay, so each parameter corresponds with a free variable, and so the matrix having rank R, the dimension of its row space being R, means that correspondingly, when you take A in reduced echelon form, you'll have R rows with leading ones. You'll have R rows with leading ones, but that would mean you'll have R columns with leading ones. And so the rest of the columns are your free parameters, are your free variables, which correspond each with its own parameter. So if there's n columns, and you have R columns with leading ones, the rest of the columns will correspond with a parameter. So total of n columns, R columns have leading ones, the rest of them don't have leading ones, those will correspond each with its own parameter. So total of n minus r other columns that don't have leading ones, those will correspond with variables that are free variables, which means each results in its own parameter. We have exactly n minus r parameters. Okay? Okay, keep going. Okay, so that's that. Okay, so there are 6 important vector spaces associated with A and A transpose. Okay, and so those vector spaces are the row space of A, the column space of A, the null space of A, the row space of A transpose, the column space of A transpose, null space of A transpose. Okay, so the row space of A, the column space of A, the null space of A, and the null space of A transpose, if you take those 4, those are the 4 unique ones. And so these 2 are repeated by the other 4. These 2 do not add any spaces to the list of 6, okay? So there are 6 important vector spaces associated with A and A transpose, but you can reduce it to 4 because these 2 are actually just repeats, okay? And so those 4 are the fundamental spaces of a matrix A. Okay, so those 4 I circled are called the fundamental spaces of a matrix A. Okay. All right, fundamental spaces of a matrix A. Those 4 are circled. Okay. Okay. Theorem 4.8.5. If A is in a matrix, then the rank of A is equal to the rank of A transpose. So theorem 4.8.5 says if A is in a matrix, then rank of A equals rank of A transpose. So the rank of A plus the nullity, so I'm just going to put some facts here, plus the nullity of A transpose is equal to M. So again, A is a M by N matrix. Okay, so I'm assuming A is an M by N matrix, and so the rank of A plus the nullity of A transpose is equal to M, the number of rows of A. The dimension of the row space of A, which I'm abbreviating by row of A, the dimension of the row space of A is equal to R. The dimension of the column space of A is equal to R. The dimension of the null space of A is equal to N minus R. And the dimension of the null space of A transpose is equal to M minus R. Okay, so this is 5, and okay, so 5 is that equation, and 6 are those 4 equations. Okay, and so these 5 equations together talk about the dimensions of fundamental spaces. Okay, right? So remember, the 4 fundamental spaces are the row space of A, the column space of A, the null space of A, and the null space of A transpose. And so these are the dimensions of the 4 fundamental spaces of a matrix A in terms of its number of rows and columns. And so A is M rows and N columns, and you can know the dimension of each of its fundamental spaces in terms of M, N, and R, where R is the dimension of the row space of that matrix. Okay? So R is the dimension of the row space of that matrix. Okay, and so we have some more facts here on this board. And again, this theorem says if A is in a matrix, then the rank of A is equal to the rank of A transpose. Okay? Which makes sense because the row space and column space of a matrix have the same dimension. And so this is basically in a way saying the dimension of the row space of A is equal to the dimension of the column space of A. Because the dimension of the column space of A is the same as the dimension of the row space of A transpose. Okay, so that's a lot. Okay, let's keep going. Let me just check one thing. Okay, I want to see if you can see what I'm writing. Might use other markers. Okay, let's keep going. Okay, so next is a definition. Okay, so definition. If W is a subspace of Rn, then the set of all vectors in Rn orthogonal to every vector in W is the orthogonal complement to W. Okay, and it's denoted by W with a perpendicular sign as a superscript. Okay, so this is the definition of the orthogonal complement of a subspace W of Rn. So if W is a subspace of Rn, then the set of all vectors in Rn orthogonal to every vector in W is the orthogonal complement to W, denoted by that symbol. Okay, the idea is this. Let's say you have, for instance, the x-axis and y-axis in R2. Okay, so we're in R2, which has the x and y-axis, and then let's say we have a subspace of R2, which is the span, which is just this line, right? The subspaces of R2 are either lines through the origin or the entire space, and so this line through the origin is a subspace of R2. So now, the orthogonal complement of the subspace of R2 is the set of all vectors orthogonal to every vector in W. Well, any vector in W is going to start at the origin and just be on this line. And so every vector in the subspace W will be on this line. And so if you want vectors orthogonal to every vector in W, just take a line perpendicular to that one through the origin. And now this line through the origin perpendicular to that line W, this is going to be the orthogonal complement of W, this line. And every point in the line represents its own vector. Okay? Every point in that line will represent the vector starting at the origin and going to that point. That will be a vector that's perpendicular to every vector on the line perpendicular to the line it's on. So if you take any vector on this line, it's perpendicular to every vector on the other line perpendicular to it. Okay? And so the line perpendicular to this line through the origin is the orthogonal complement of that line through the origin. And that's the example of the orthogonal complement of a subspace of R2. Now if you look at R3, here's the x-axis, here's the y-axis, and here's the z-axis. And so now here's 3 space. And so now let's take a plane going through the origin. So if we take a plane going through the origin, then here's the plane. It's going through the origin, right? It's having fun. And here's our subspace W of R3. It's a plane through the origin. It's a subspace of R3, right? All the subspaces of R3 are lines through the origin, plane through the... So actually, I should include the 0 set as a subspace. So sorry. The subspaces of R2 are either the point 0 itself, lines through the origin, or all of R2. The subspace of R3 is just the point at the origin, lines through the origin, planes to the origin, and all of R3, right? A previous lesson I told you what the subspaces of R2 and R3 are. Okay, so this plane through the origin is a subspace of R3, and if you wanted to know its orthogonal complement, the orthogonal complement of that plane in R3 through the origin, which is a subspace of R3, just take a line perpendicular to that plane. Just take a normal vector to the plane that goes to the origin. Well, if you were to take a normal vector to the plane, it would be the line through that normal vector. Okay, and so a line perpendicular to that plane, so this line, this is the orthogonal complement of that plane through the origin.
It's just a line perpendicular to the plane. And that means any vector on that line is perpendicular to the plane, meaning that if you take any vector on the plane, then any vector on that line is perpendicular to every vector in that plane. So if I put any vector on the plane, then a vector on this line would be perpendicular to it. For instance, if I thought of this table as that plane, but instead of slanted, it was just like a table, like flat like this. If I thought of this marker sitting perpendicularly to the plane, right, you would intuitively say that this thing standing up was perpendicular to the surface of the table. And what that would mean here would mean if I started with the vector starting at the bottom of this pen and I just drew a vector on the table, that vector would have to be perpendicular to to this marker itself. It would be perpendicular to it, right? 90-degree angle between this and that. But I didn't have to draw that vector. I could have drawn any vector on the table, and it would still be perpendicular to any to this marker. Okay, and so, but since this is slanted, it's like the table was slanted, and then this would then just turn with it, and so this would be slanted, but it would still be perpendicular to that surface, just like this line is perpendicular to that plane. Okay. Okay, so these are two examples of the orthogonal complements of subspaces R2 and R3 respectively. Okay, and so that's the definition of the orthogonal complement of a subspace W of Rn. Here n is 2, there n is 3. Okay, let's keep going. So theorem 4.8.6. Theorem 4.8.6. If W is a subspace of Rn, then A, the orthogonal complement of W, we're using this notation, right, from the definition, is a subspace of Rn. So in our previous examples on the last board, when we found the orthogonal complement of each space, we're actually finding another subspace of the Rn that it was in. Right, so the line in the first example, its orthogonal complement was another line, which is also a subspace of R2. Here, I gave a plane, which was a subspace of R3, and its orthogonal complement was a line. That line was also a subspace of R3. And so the orthogonal complement of W is also a subspace of Rn. Okay, and B, the only vector common to W and its orthogonal complement is 0, right? And hopefully, and that might make sense, right? Because if you take a subspace W, its orthogonal complement, it only consists of vectors perpendicular to every vector in W, right? And most vectors are not perpendicular to themselves. The only vector that's perpendicular to itself is the 0 vector. And so in order for a vector to be both in W and W complement, it would have to be a vector that would be perpendicular to itself, right? Because the vectors in these spaces are perpendicular to each other. And so it being in both means you can only have a vector whose perpendicular was itself, which is perpendicular to itself. Only the 0 vector is that. And so the 0 is the only vector in both subspaces, in both W and W complement. Okay, C, the orthogonal complement of the orthogonal complements of the orthogonal complement of W is W. Okay, what C is saying is that if you take the orthogonal complement of the orthogonal complement of W, you get W. That's what C is saying. Okay, and B, just writing this, the intersection of W and W complement is equal to the 0 set. Okay, that's the only point they have in common. And so in shorthand, this is what B and C are saying, respectively. So that's theorem 4.8.6. And now theorem 4.8.7. If A is n by n, then A, the null space of A and row space of A are orthogonal complements. In Rn. Okay? Okay, so both the solution vectors of Ax equals 0 and the rows of A are both in Rn. Okay? And so the null space of A and the row space of A are orthogonal complements in Rn. Okay? And so the idea of that is if you have the null space of A are the solutions of Ax to Ax equals 0. The null space of A are the set of solutions x to Ax equals 0. But what that's saying is that if you take the rows of A and you multiply them with any solution, you get 0. And so if you take, so what this says is that A, right? A is a matrix consisting of a certain number of m rows, R1, R2, so Rm. Okay? And so those are the m rows of A, and then you're multiplying it by a solution, x1, x2 to xn, and you're saying that equals the 0. Okay? So what that means is if you multiply these matrices, let's say you multiply the first row R1 by all these x's, you're going to get 0. If you multiply the second row of A by this, you get 0. If you multiply the third row by this, you get 0. If you multiply the mth row of A by this, you get 0. That means all the rows of A are orthogonal to any solution, to Ax equals 0. The solutions, these vectors x here, that's a solution. That means this vector x is orthogonal to every row of A, because if you take multiplying this by this is the same as saying the dot product of a row and x. If the dot product of a row vector of A and that is 0, that means they're orthogonal. Okay, so every solution to Ax equals 0 is orthogonal to every row of A. So the null space of A and the null space of A are orthogonal complements in Rn. They're each vectors in Rn that are orthogonal to each other. Each space consists of vectors in Rn that are orthogonal to each other. So those two spaces are orthogonal complements of each other. Okay, and then B is the null space of A transpose. The null space of A transpose and the column space of A are orthogonal complements. Are orthogonal complements in Rm. So null space of A transpose and the column space of A are orthogonal complements in Rm. Okay. So if you take the transpose of a matrix, right? If you take A transpose x equals 0, the null space of A transpose is the set of all solutions x to A transpose x equals 0. And so the solutions x to A transpose x equals 0, the solutions x are orthogonal to all the rows of A transpose. But the rows of A transpose are the columns of A. And so every solution to A transpose x equals 0 is orthogonal to every column of A. And so the null space of A transpose is orthogonal to the column space of A. If you take any solution to A transpose x equals 0, it's orthogonal to any column of A or every row of A transpose. Okay, and so that's B. Okay. Right, and the columns of A and the solutions to A transpose x equals 0, those are both vectors in Rm. Rm, because there's m rows in A. Okay? Okay. So one more theorem for 4.8. Okay, so theorem 4.8.8 is the equivalent statements theorem, but we've already seen the equivalent statements theorem before, and And so this is just adding on, adding to this theorem. Okay, so the equivalent statements theorem says if A is n by n as a matrix, then the following are equivalent. So TFAE is shorthand for the following are equivalent, or the following have the same truth value. So all these statements have the same truth value, and some of them are written down, right? A is invertible is part A. That's equivalent or has the same truth value as statement B. AX equals 0 has only the trivial solution. Right? So AX equals 0 having only the trivial solution means that the only X that satisfies AX equals 0 is X equals 0. Part C is the reduced echelon form of A is I sub n. Okay? So if you take the matrix A and you get to reduced echelon form, you'll get the n by n identity matrix. That's statement C. That's equivalent to all these statements. D is A is expressible as a product of elementary matrices. Okay, so A is expressible as a product of elementary matrices. E, AX equals B is consistent. For every n by 1 matrix B. Okay, and so that's statement E, that's equivalent. Statement F, AX equals B has exactly one solution. For every n by 1 B, n by 1 matrix B, for every n by 1 matrix B. G, the determinant of A does not equal 0. H, I'm gonna put H over here because I'm running out of room. So H I'm gonna put here. H is the column vectors of A are the column vectors of A are linearly independent. Okay, so the column vectors of A are linearly independent. That's part H. Part I is the row vectors of A are linearly independent. Okay, so part I is the row vectors of A are linearly independent. J is the column vectors of A span Rn. Okay, so the column vectors of A span Rn. That's statement J. Statement K is the row vectors of A span Rn. The row vectors of A span Rn. So the row vectors of A span Rn, that's statement K. L, so statement L is the column vectors of A so the column vectors of A form basis for Rn. Okay, so that's statement L, the column vectors of A form basis for Rn. Okay, and I'm going to have to erase this to add the other parts. So this is A through L, and they're equivalent. And on the next board, with the same hypothesis that A is an n by n matrix, I'm going to continue that with more equivalent statements. So that's statement L. Okay, so these are the A through L. These are all equivalent, and they're going to also be equivalent to the next statements I write down. So after L is M. So statement M is also equivalent to all those statements. For an n by n matrix, A. So statement M, continuing the same theorem, is the row vectors of A form basis for Rn. So the row vectors are form basis for Rn, sorry. Rn, okay. And then element O, LM, N, okay. N is, A has rank N. A is nullity 0. P, the orthogonal complement of the null space of A is Rn. Of the null space of A is Rn. So the orthogonal complement of the row space of A okay, so Q is the orthogonal complement of the row space of A is the 0 set. Okay, so all of these statements A through Q are equivalent. They have the same truth value, assuming that A is an m by n matrix. Okay, and that's the end of the equivalence theorem up to this point. Okay, and there's actually even more statements we're going to add to this theorem in the future. It will go past Q. We'll go from A to Q, and then we'll keep going. But at this point, the end of 4.8, we are up to that part of the equivalence theorem. So right now we're done with 4.8. Okay, and so I'm going to put a second video, part 2 of this lesson. It's the same lesson, I'm just going to break it up into 2 videos because it's very long. So the next part 2 you'll watch, we're going to continue 4.9 and then 4.10. Okay, see you soon.